Okay, in this video we are going to prove a characterization of two chromatic graphs. So the statement reads as follows. So a graph is two chromatic or bicolourable if and only if it has no odd cycles. So before proving this statement, let's look at one or two examples. So the statement reads, if a graph is bicolourable, two chromatic if and only if it has no odd cycles. So let's consider these two graphs. Let's call this graph G and H. Okay, here we can see that this graph is G is two colorable. Okay, moreover, and again we can see that the chromatic number, the chi of G is equal to 2. Okay, because since it has at least one edge, and again we can see that if you look at this assignment of colors, it is a proper one. Okay, and if you look closely at this graph, we can see that it has only even cycles. Okay, one cycle is something like this. This 1, 2, 3, 4. Another cycle is this and this. Okay, again cycle of length 4, which is even, and the outer cycle 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. So that outer cycle it do have length 6, which is even. Okay, and okay, I think one more cycle. Okay, this one, okay, this one, and that. Okay, so we can see that if you consider any cycle in this graph G, all the cycles have even length. And if you believe in this statement that says a graph is bicolourable or two chromatic if and only if it has no odd cycle. So if every cycle is even, then the graph is definitely bicolourable or two chromatic. Okay, so at least we saw that from this example. Okay, let's look at this particular graph. So if you look at this particular graph, we can see that here, okay, we have a triangle here. Okay, so that says at least this particular cycle have odd length. So that says okay, it is not two colorable. So if you believe in this particular statement, that says this graph it is not two colorable. Okay, and again we can see that from this assignment. Okay, we can see that it can only be colored with 3 colors. For example, if you assign color 1 here, okay, these two vertices are adjacent, so they must be given a different color. So let's take this vertex and give color 2 to that vertex. So we can see that this vertex, okay, is adjacent to this 1 and 2, not 1 and 2, okay, these two vertices which are colored 1 and 2. Okay, and that says we need to use a different color, something like 3 here. Okay, so that says we need at least 3 colors for coloring this graph. Okay, we can see that it could be colored in with using 3 color as shown in this assignment. Okay, so okay, here this you can see that chi of or the chromatic number of H, okay, that is 3. Okay, so let's go and prove the statement. So that says a graph is bicolourable or two chromatic if and only if it has no odd cycle. So it is in if and only if form, so we need to prove two directions. The first direction is if a graph is two chromatic, then it has no odd cycle. The other direction is if a graph has no odd cycle, then the graph is bicolourable. Okay, so let's go and prove the first direction first, and then the other one. Okay, so we are going to prove this statement. If a graph G is two chromatic, then it has no odd cycle. Okay, so let's go and prove that statement first. Okay, so let G be a graph that is bicolourable. Okay, so let G be a bicolourable graph. Again, we want to prove that G has even cycles only. Okay, so we want to prove that G has only even cycles. Okay, so we are going to prove the this direction by contradiction. So we assume that G has at least one odd cycle, okay, and we will get a contradiction, and that says G has only even cycle. Okay, so assume to the contrary that this graph G has an odd cycle. Okay, so see, assume that G has an odd cycle. So that says it has a cycle Cn where n is odd. Okay, we know that if we consider a cycle of with n vertices, okay, the chromatic number is equal to 3 if this n is odd. Okay, so if it has a odd cycle, then the chromatic number is, okay, for a cycle we know that the chromatic number is equal to 3 if the number of vertices is odd. Okay, if the number of vertices is even in that cycle, then the chromatic number is 2. Okay, so we know that the chromatic number of a cycle of odd number of vertices is 3. Okay, and we are assuming that G has an odd cycle. So it says, okay, this particular graph G has a cycle Cn where n is odd as a subgraph. Okay, and we know that if you consider a graph, the chromatic number of that graph is always greater than or equal to the chromatic number of a subgraph. Okay, so we know that this is at least 3. Okay, if n is odd. Okay, it is 3. Okay, and that says for an odd cycle the chromatic number is, okay, as I said here, the chromatic number is 3. Okay, and that says this G is 2 colorable. Okay, and not 2 colorable, at least 3 colors are needed for coloring this thing. Okay, and it is 3 colorable if we assume that G has an odd cycle. So that says, so D is 3 colorable. Or at least we require 3 color. Okay. So G is 3 colorable. Okay, and that is a contradiction. Okay, 3 is at least 3 colorable. So here we assume that G is bicolorable. Okay, and if you assume this particular thing, G has an odd cycle. Okay, so odd cycle, the chromatic number is 3. So that says this graph has chromatic number at least 3. Okay, and that says this graph okay, is not a bicolorable one, but we assume that, okay, we started by this hypothesis, G is a bicolorable graph. So we get a contradiction, and that says our assumption is wrong. Okay, this assumption is wrong. So that says every cycle in the graph has even length. Okay, so hence G has now odd cycle. Okay, so that's the proof for the first part. So we proved if the graph is bicolorable, then it has no odd cycle. So let's go and prove the other direction. So conversely, okay, so we are going to prove this one. If the graph has no odd cycle, then the graph is bicolorable. So let's go and prove that one. Okay, and conversely assume G is a connected. So only need to prove for a connected graph. So if the graph is disconnected, then apply the argument, the following argument to each and every connected component, and that will give you the proof for disconnected graph. So only need to prove for a connected graph. So conversely assume G is a connected graph with cycles of even length. Okay, with only cycles of even length. Okay, so let's consider a spanning tree of this graph T. Okay, so let T be a spanning tree of G. So from the previous video we know that any tree is two colorable. So this spanning tree is also two colorable. Okay, and that says since every tree is two colorable, this spanning tree T can be colored with two colors. Okay, now what we are going to do is we are going to add the remaining edges, the chords, back into this tree until we get the original graph. Okay, so here we are assuming that it's a connected and only cycles of even length. Okay, so the situation is something like this. So we have this spanning tree. So we know that this spanning tree is two colorable. Okay, so that says if you assign color 1 here, okay, at this level we all the vertices will have 2, and at this level all the vertices will it could be colored 1, okay, 1 etc. In the next level we color with 2, 2, okay, and in the next level we will color with 1 etc etc. So at the even we consider this as a root, say V. Okay, odd distance from all the nodes which are at odd distance will be colored 2, and at even distance including this V will be colored. For example, okay, this is at even distance 0. Okay, all these vertices are at distance 2. Okay, all these vertices are at the distance 3, 4 etc. So these two levels are at 2, so they will be colored 2. Okay, all the events will be colored 1 and so forth. Okay, and since we assume that this graph G doesn't have any odd cycle, so that says it will not have a chord that goes from two vertices at the same level. Okay, the same level in which we get an odd cycle. For example, if we add these two, we get a triangle. Okay, and that says we have an odd cycle in our graph, but that is not allowed because our assumption is that the graph has only even cycles. Similarly, there won't be an edge from a different, okay, from here to here also. If that's the case, then we will have 1, 2, 3, 4, 5. Okay, so that will violate this thing. Okay, we will only have okay edges from this one to that one. Okay, something like that. Okay, so let me write down what I said. Since every tree is two colorable, T can be colored with two colors. Okay, so next part we are going to do is we are going to add back the codes into this tree until we get our original graph. So now add the codes to T one by one. okay, until we get our original graph G. And since G has no odd cycle, every cycle is even, the n vertices of each chord get different colors, okay, and that's what we can see from here. Okay, since G have only even length, so that says there won't be an edge from the nodes at the same level or same distance from this V. Okay, only we will have edges from here to here or something like that, from here to here or something like that. Okay, so we always get, okay, when we add an edge, we always get the situation something like both the n vertices will have colors of opposite colors. Okay, and the reason is we are assuming that the graph it has only even cycles. Okay, so now add the code to T one by one until we get this G back. Okay, till we get the graph G. Okay, so we can very easily see that as G contains cycles of even length, the n vertices of each chord will get different colors. Okay, so anyway we saw from that example. So as G contains only cycles of even length, the n vertices of each chord gets different colors. Okay, and that says the graph is okay. Anyway, we started with a tree. Tree is two colorable, and when we add this chord, and because of this reason, only G contains only even length cycles. Okay, adding a chord, it won't violate the condition that two adjacent vertices will get same color. Okay, because adding a chord, the n vertices will get different color, and that is true for each chord, since the graph contains only cycles of even length. Okay, so as G contains only cycles of even length, the n vertices of each chord gets different color. Okay, so that color constraint is not violated. Okay, and thus G is colored with two colors and have a two coloring, and then it is two chromatic. Okay, and thus G is colored with two colors, and hence G is bicolorable or two chromatic. Okay, and that's what we want to prove. So we are able to prove both direction, and that says a graph is bicolorable if and only if it has no odd cycle.